The discussion on area of surface of revolution is actually a continuation of the discussion on finding the length of the arc. Okay, now if we will consider a curve, okay, let us say given by y is equal to f of x, if we will revolve this about an axis of revolution. Okay, let us say that the axis of revolution is the x-axis. Then the surface that it generates is what we call as the surface of revolution. Okay, so the green shaded area here is what we call as the surface of revolution. And we can determine the surface of revolution by using the formula S, which is the surface of revolution, is equal to 2 pi times the integral within the limits of integration of L times the differential of L. Okay, now please take note that the differential of L is the differential of the arc length. Okay, the arc length L. And take note that during the discussion of the arc length L, now finding the length of the arc L or L, which is the which will depend, of course, on the given function, whether y is equal to a function of x or x is a function of y, or if we have parametric equations, x and y in terms of the parameter t, or if we have a polar equation, okay, then we can use those formula for the differential of L. And L is the distance of the element of arc dl, the differential of L, from the axis of revolution. So for example, if we consider part of this, rotating this about the x-axis, then the distance of this point from the differential of L, rather, from the axis of revolution is L. So L is the distance of the element of arc length differential of L from the axis of revolution. Now, the first formula is when y is equal to a function of x, now, which defines a function whose curve is continuous within the closed interval from a to b. Now, take note that the differential of L when y is equal to a function of x is the integral from a to b of the square root of 1 plus the square of the derivative of y with respect to x, okay, from a to b. And we have to, since we are getting, or we will determine the area of surface of revolution S, then we will just multiply it by 2 pi L, which is actually the circumferential, the circumference. Okay, so the surface of the surface of revolution, or the area of surface of revolution when y is equal to a function of x is 2 pi integral from a to b, okay, L times the square root of 1 plus the square of the derivative of y with respect to x. And we will evaluate the integral in x. Now, on the other hand, if x is a function of, it is a function of y, then the surface area, or the area of surface of revolution, if x is equal to g of y, is a continuous function within the interval from c to d. So S is 2 pi times the integral from c to d of, okay, L times the square root of 1 plus the square of the derivative of x with respect to y. And of course, the integral will be evaluated in y. Now, if we have parametric equations, okay, x and y in terms of t, the parameter t, then we need to find the derivative of x with respect to t and the derivative of y with respect to t. And we have to make sure that it is continuous within the interval from t1 to t2. And the area of surface of revolution is 2 pi, okay, times the integral of L times the square root of the square of the derivative of x with respect to t plus the square of the derivative of y with respect to t, limits going from t1 to t2. Of course, this must be evaluated with respect to t. And if r is a polar equation, no, r as a function of theta, in polar coordinates and continuous within the closed interval from theta 1 to theta 2, then the area of surface of revolution is 2 pi integral from theta 1 to theta 2 of L times the square root of r square plus the square of the derivative of r with respect to theta, okay, integrated with respect to theta. Now, to illustrate how to find the area of surface of revolution by integration, then we will consider two examples here. Okay. And the first one is we will find the area of surface of revolution generated by revolving about the y-axis. Okay, that part of the curve y is equal to x squared from x is equal to 0 to x is equal to 1. Now, if we will consider generating about the y-axis, so the y-axis is the axis of revolution. Therefore, the distance of the differential of L from the y-axis is x. So L is equal to x. And since we have y is equal to x squared, we have a parabola opening, part of the parabola opening upward from x is equal to 0 to x is equal to 1. Then we need to get the derivative of y with respect to x, which is equal to 2x. Okay, so derivative of y with respect to x is equal to 2x. And since we will find or determine the length of, or sorry, rather the area of surface of revolution, the area of surface of revolution, since we have y as a function of x, is 2 pi times the integral of L times the square root of 1 plus the square of the derivative of y with respect to x, okay, dx. And x will go from 0 to 1. Take note that the variable of integration is x, and the curve is continuous within the closed interval from 0 to 1. So lower limit is 0, upper limit is 1. Now, since the y-axis is the axis of revolution, then the distance of the differential of L from the y-axis is x. Hence, this will give us 2 pi integral from 0 to 1, L is equal to x, square root of 1 plus the derivative of y with respect to x is 2x. Okay, we raise this to the second power and we will evaluate the integral in x. Hence, s is equal to 2 pi integral from 0 to 1, okay, x square root of 1 plus 4x squared dx. And we can evaluate the integral by power formula, but then we have to express the radical in exponential form. Okay, so 2 pi integral from 0 to 1 of the square root of 1 plus excuse me, I should have expressed this in exponential form. So we will have quantity 1 plus 4x squared raised to 1 half, and then we have x dx. Of course, to evaluate this, we can let u is equal to, okay, we will let u is equal to 1 plus 4x squared, so that the differential of u is du, and the differential of 1 plus 4x squared is 8x dx. So there must be a correction factor 1 over 8. No? We can just introduce 8 here and write the reciprocal 1 over 8 before the integral sign. Hence, okay, so to continue, then s is equal to, I'm writing, moving to the left, not to create more space. Okay, we can actually do cancellation here, since the correction factor is 8. Okay, 2 by 8, no, or both are divisible by 2, so we will simply have pi over 4. Okay, and by power formula of integration, no, then that gives us 1 plus 4x squared raised to 1 half, plus 1 is 1 over 3 over 2. Okay, so 3 over 2 over 3 over 2. And we have to evaluate this from 0 to 1. Okay, now the reciprocal of 3 over 2 is 2 over 3. So we can simply have pi over 4 times 2/3, okay? And we can now evaluate 1 plus 4x squared raised to 3 over 2 from 0 to 1. And here, if we will do cancellation again, no? Okay, we can cancel 2 and 2 here. So that will give us pi over 6. Pi over 6, okay, times. And when x is equal to the upper limit 1, okay, then that will give us 1 plus 4, which is equal to 5, square root of 5, okay, raised to the third power will give us 5 square root of 5. Okay, then minus, when x is equal to 0, then that will give us 1 raised to 3 over 2, and 1 raised to 3 over 2 is 1. So we have the area of surface of revolution equal to pi over 6 times the quantity of 5, square root of 5 minus 1. Okay, so this gives us the length of the arc of the parabola. Part of the parabola y is equal to x squared from x is equal to 0 to x is equal to 1. So the surface, or the area of surface of revolution, is pi over 6 times the quantity 5 square root of 5 minus 1. Okay, so that's it. Let us now consider the second example. And this time, we will consider finding the area of surface of revolution generated by revolving about the y-axis. Okay, the curve x is equal to square root of 9 minus y squared from y is equal to 0 to y is equal to 2. Okay, by the way, this problem, okay, this is also actually the problem in the lecture notes. In the lecture notes, okay, the surface is, or the curve is from x is equal to 0 to x is equal to 2. Okay, there is a correction here. So instead of x is equal to 0 and x is equal to 2, it must be y is equal to 0 to y is equal to 2. Okay, so we have to consider x equals the square root of 9 minus y squared. We have x as a function of y. Hence, if we will get the derivative of x rather, with respect to y, okay, by power formula, by the special formula, no, we have the derivative of 9 minus y squared is negative 2y over 2 times the square root of 9 minus y squared. And of course, we can cancel 2 so that the derivative of x with respect to y is equal to negative y over the square root of 9 minus y squared. Okay, now, since the axis of revolution is the y-axis, then again, L is equal to x. The distance of the differential of L, okay, from the y-axis is x. But of course, if we will make this as the axis of revolution as the x-axis, then the distance is y. Okay, now, how do we get the area of a surface of revolution when x is a function of y? Now, the area of surface of revolution when x is a function of y is 2 pi integral from c to d, okay, of L times the square root of 1 plus the square of the derivative of x with respect to y. And the variable of integration, of course, is y. Hence, this will give us 2 pi integral of, okay, L is x, okay, L is equal to x, and we have the derivative of y with derivative of x with respect to y is negative y over the square root of 9 minus y squared. So this will give us 1 plus the square of negative y over the square root of 9 minus y squared dy. Okay, limits going from y is equal to 0 to y is equal to 2. Hence, the area of surface of revolution is 2 pi integral from 0 to 2 of x. Okay, since x is must be written rather in terms of y, then we have to replace x by the square root of 9 minus y squared. Take note that the variable of integration is y, so we have to write the integrand in terms of the variable y. Okay, so times the square root of, okay, this must be square. Okay, sorry for that. So plus 1 plus the square of negative y over the square root of 9 minus y squared is y over 9 minus y squared times the differential of y. And if we will simplify the radicand, okay, 0 to 2, we have square root of 9 minus y squared, okay, times. We can actually get the common denominator, and the common denominator is 9 minus y squared. Okay, just focus on the radicand first. Okay, 9 minus y squared. So we will have 9 minus y squared, right? Okay, and sorry for this. This must be square. Okay, negative y raised to the second power is y squared. So plus y squared dy. Okay, now negative y squared plus y squared will give us 0. Hence, the integrand is now reduced to square root of 9 minus y squared times, okay, since the numerator in the radicand okay, is 9, since negative y squared plus y squared is 0. Then we will have square root of 9 over the denominator, which is also equal to square root of 9 minus y squared. Take note that we use here the property of radicals. We can express the square root of 9 over 9 minus y squared as square root of 9 over the square root of 9y minus y squared dy, such that we can now do a cancellation. We can cancel this, okay? And this will simply give us 2 pi integral from 0 to 2. The square root of 9 is 3 times the differential of y. Okay, and we will have 2 pi times 3 is 6 pi, and the integral of the differential of y is y, and we need to evaluate this from 0 to 2. Hence, we will have 6 pi times, when y is equal to the upper limit 2, we have 2 minus, when y is equal to the lower limit 0, that gives us 0. Therefore, the area of surface of revolution is equal to 12 pi. Okay, so we have S is equal to 12 pi square units. Okay, so since we know how to get the length of the arc, it will not be hard for us to find also the area of surface of revolution. We just multiply the differential of L by 2 pi L, where L is the distance of the differential of the arc length from the axis of revolution. And to help you familiarize in solving area of surface of revolution, you may also consider working on these examples or exercises. Find the area of surface of revolution when revolve about the x-axis. Okay, please take note that when the arc is revolved about the x-axis, the distance of the differential of the arc from the x-axis is y. Okay, and when the axis of revolution is the y-axis, the distance from the axis of revolution is x. Okay, so that's it. Okay, this is how to get the area of surface of revolution. If x is equal to a function of y, then this is the formula. Okay, if we have parametric equations, x and y in terms of t, and if we have a polar equation in polar coordinates rather. And of course, if we have y as a function of x, then to compute for the area of surface of revolution, we use this formula. And in general, to compute for the surface of area of surface of revolution, we use the surface of area of surface of revolution S is equal to 2 pi integral within the limits of integration, the interval of L times the differential of the arc length.